Hi students, welcome back to Mpmc Lab. So in today's video we will see the experiment 2 programs for 16-bit arithmetic operations of 8086. So we can write these programs in any one of the addressing modes. So first we will see the register addressing mode, and the first arithmetic operation we are going to see is addition. So first we will go with addition, right? Assembly language program to add two 16-bit numbers. So in the previous experiment we have seen 8-bit numbers. Now we need to consider 16-bit numbers. So let us start the program. The first statement is assume CS code DS data. We require code segment and data segment. We have given names for these code segment as code, data segment as data. So now let us write the content of the logical segments. First, data segment, right? So what you need here we need two 16-bit numbers, and after adding these two you are going to get one more number. So you require or you need to allocate memory for three numbers, and those are 16-bit, right? So first let us consider number 1. This is the variable name given to number 1, and you need to define it as word, define word, because it is a 16-bit. So let us consider a number 4343h. So in the same way, let us consider variable for number 2 as n2, and which is also word, define word 6767h. Any number you can consider here, but the size, maximum size must be 16-bit. And one more variable, that is n3, to store the result. So as of now we are initializing it with a question mark. For our understanding, question mark indicates you need to update this value of n3. So that's it. This is the end of the data segment, data logical segment. End S stands for end of the segment. Next we need to start the code segment. In fact, I need to write here, but I am writing here. Code segment, code space segment. This is the syntax we need to follow. Then I am using a label start to indicate the starting of the code. As I said, we need to write these two lines in order to use data segment in our program, because you need to access this n1 and n2, and you need to load the result into n3. For that reason, you need to initialize the data segment starting address to ds. Okay. Next, now I need to use register addressing mode. Okay, so move ax comma n1, move bx comma n2. So what is happening here? Ax is loaded with n1, bx is loaded with n2. So then simply you can use now the add instruction ax comma bx. Then what will happen? Ax will be loaded with the content of or the result of ax plus bx, right? Now we need to load this result back to n3 location. In fact, these variables are nothing but the names which are given to the locations, right? So n3 is a variable that is nothing but a location, the result location. Move n3 comma ax, right? Now we don't know this n3 location exact value. To know that, you can use LVA, load effective address of n3, into SI. So after this instruction, whatever the SI content, that is nothing but the address of the result. Then we can use debug breakpoint int 3h. Then end the code segment. This is the end of this particular logical segment. Then end the entire program and start, because the program is started with start variable, start label, sorry, it is a label. So you need to end that, end start, right? So let us see the compilation, the manual compilation. AX is 4343H because of this, and next BX is 6767H. Then this instruction will be executed. So now AX will become 7 plus 3 is 10, 10 is decimal, in hexadecimal it is A. 6 plus 4 is also 10, that is A, and A. And this is the final result of AX. And when you execute this program, you will come to know what is the value of SA. Okay, mostly it will be like if this value is started with a 00H location, all 0 location, and this will become 002H. Why? Because this is DW, that means here 2 bytes will store, one byte at 000H and other byte at 0001. So next N2 will start at 0002, and 3 will also be used for N3. Next this will become 004H. So this particular 004H will be loaded to this SI in general. If randomly, if you are starting with any other origin, if you are using some ORG instruction, in that case these values may differ, right? Now from this result, this result will affect few of the flags. Those are carry flag and one more is parity flag. Of course the overflow flag and sign flag will also will affect, but because we are doing some unsigned operation, unsigned binary numbers, because these 4343H and 6767H are in our consideration, these two are positive, so you need not to look at this sign flag, right? The carry flag, here the carry flag is 0. Why? Because when you add this AX BX, there is no carry generated at MSB. That means 6 plus 4 is A. If it is generating any carry at this position, then this CF flag will become 1. And parity flag, in order to check in order to find out the what is the parity flag status, you need to write down this particular result in binary form. So A stands for 1010, because you have all A's 1010, 1010, 1010, and in one A you have 2 ones, here 2 ones, 2 ones, 2 ones, total you have 8 ones, and 8 is nothing but even number, so indicate even, the parity flag is 1. In 8086, if the result is consisting of even number of ones, the parity flag will become 1, right? So this is addition of 16-bit numbers.